Yes, so it's with great pleasure today that I'm with you to share basically the results of about 6 years of experiments doing forestry and AI. This is not
Maybe you
all the
can
work.
share your screen first.
Oh, sorry. Yes,
Yep,
sorry.
no
And there
worries.
we go. Yes,
Yep,
good.
got it.
And so yeah, so we're a lab that does a lot of outdoor robotics, but some of it is of interest to the forestry industry and forest researchers. So that's what I'm going to be talking today about. So starting here. Okay, yes. So NorLab, we are a lab that specializes in doing field robotics in harsh weather conditions. You see at the top here, winter condition, for instance. We also do research with unstructured environments. So we don't do self-driving cars in the city. We like to work in places like the forest, the boreal forest, because we have access to this kind of forest near our lab. And also we work with GPS denied environments. For instance, my colleague François Pomerleau, he participated in the DARPA Sub-T challenge, where they had to deploy a fleet of robots autonomously in underground conditions. And obviously underground means GPS denied. But all of these conditions are also very common in forestry. And that's why we teamed up with FORAC, which is a research consortium here at Laval University that does research in collaboration with the forestry industry. So today I'm going to talk, the first part of the talk will be quickly describing some of the projects we've done, both in terms of 3D, like LiDAR sensing, but also AI, like using cameras to find semantic information about the world. And then the second part of my talk, I will go over about 9 lessons learned over all these years, which I think is the most important part of this talk. So we've done work 3D mapping. This is, I think, one of the first applications that people foresee for 3D LiDAR like many years ago. So in 2019, we equipped one of our mobile robot that you can see here in the middle. So it's driven by Jean-François Tremblay. So it's not autonomous right now, it's driving it. And we have a 32 beam LiDAR that was known by the space agency at the time. And with that, we collect a bunch of scans, and then using what's called a SLAM algorithm, is we stitch a little bit like a puzzle. We stitch all of the 3D scans together, and then we are able to build a complete 3D map of the environment. And once we have this 3D map, then we can go and be able to extract some measurements in the 3D scans. For instance, here we extract point clouds, which are nearby the breast height. So breast height is about 1.4 meters. And then using all these points, we fit a number of cylinders, in our case, maybe 3 cylinders, and then we take the median value. And then we can estimate the diameter at breast height of each of the tree that way. We get about 3.5 to 2.5 centimeter accuracy, but nowadays with sensors with higher beam counts, for instance, 128 beams, and also better SLAM algorithms, you probably can get down to sub-centimeter precision for DBH estimation. We also looked at doing tree species identification from bark images. So why using bark images? First of all, we thought it was an interesting scientific question. And second is bark is always present regardless of the season. So for deciduous trees that lose their leaves, then it's harder to do species recognition, but the bark is always present. But also once you cut the tree and you have logs, then again, the bark is mostly present. So that way it's a good way to be able to identify the species of your logs. So if you do deep learning or machine learning, you always need a data set. So the first step of that project was to collect a number of images. So you see about 23,000 images over 23 trees. However, only 20 trees had enough pictures to actually do machine learning on them. We have about, maybe between the 15, 20 to up to, I see like 109 trees here. And we took several pictures of the same trunk because we're there and it's just a very, very efficient way of collecting data. So we called that dataset BarkNet 1.0, which is available here at that link. And using a simple ResNet, because at the time in 2018, ResNet was the best technique. We got about 98% precision over 20 species, which we were actually quite surprised of the quality of the results. We now also are interested in finding the tree species, but this time looking at the whole picture. So it's a project related to urban forestry. So if you want images from dash cams or images from Google Street View, then are you able to find tree species using these images? And this is a PhD work by Vincent Grandin. And he's also, so you see, for example, you see here the three best predictions for this tree, like so a pine tree, I believe. Then another example here for a maple, and so on and so forth. But what's interesting with his work is he's trying to do what's called hierarchical prediction classification. So you see, for this case here, these three predictions are related to the species. So he downloaded essentially 500,000 images from iNaturalist, and over 174 species which can be found on the east side of the North America. We have about 96% precision. And as we get a bit more generic, so the genus, we have 65 genus with about 98% precisions. And if you go all the way up to the family, we have 35 families in the data set, then you get 98% precision. So the network is able to do these hierarchical prediction, because sometimes you're interested into the species, but sometimes the family might be enough for the task you want to accomplish. Maybe, for instance, the type of the quality of the wood, or is a family which will be problematic for houses or power lines, for instance. He also looked at doing crown segmentation, trunk and crown segmentation from video images. And then you can see some of preliminary results we have. So these were trained about a few weeks ago using drone images. So you see the drone flying right now, and you can see that the network is more or less able to, most of the time, capture the crown of the tree. So that way you can get better information about the environment. We also have a project right now with the Ministry of Natural Resources and Forests in Quebec. And the idea is once you cut the forest enters now a regrowth phase. And sometimes species come and will populate the area very quickly, like raspberries or ferns. And because of they grow so fast, they will actually block the sunlight and prevent young trees from growing. And what happens is 15 years later, you go to the area and the forest has not started to regrow because it's just been invaded by all these fast growing species. So the ministry is interested in finding a way to automate the diagnosis of these regrowth region. And one thing that we don't want to do is start labeling images. So what we did is it's a bit the same. It's the same idea that was published recently in June 2024, which is to leverage, again, iNaturalist, so citizen science images, and we train a image classifier, and then we can take a crop of your drone image, and for instance here, and then you see the close-up view. So this is a mountain maple. So you pass it through the classifier that has been trained with iNaturalist images, and then you have a classification. And then here's another crop. Here you have white birch. And the idea is using a sliding window, you will go over the whole image and basically transform your classifier into a semantic segmentation, a very crude semantic segmentation. So this is the kind of results that we got. So it's very blocky because we're moving the window by about 16 pixels at a time. And then we do because the patches there will be several windows over the same patch, then we do a majority vote to improve the results. But this is not the final result that we want to obtain. These are more or less pseudo labels, and we want to use these pseudo labels to then train a segmentation network like Mask2Former, for instance. And that should kind of eliminate all this salt and pepper noise that you see here and results in much clearer boundaries. So this is a work in progress. So I don't have result yet to show you, except that we have good indications that it will work for this kind of project. Another important part of the research we're doing is related to the automation of basic forestry operations. And one thing, because today we are all roboticists, and one thing that I saw when I looked at the forestry equipment is essentially mobile manipulators, giant grippers that has what we call in our language parallel grippers. So essentially a hand with usually 2 fingers. Here it's 4, but it's essentially they're parallel because they're opposite. And we had already done research with doing AI with parallel grippers, but for small objects. But here is just, the objects are just bigger and the machine is bigger. Essentially, the machine is able to kill you. So that's why you have to be a bit careful. But the idea was to transfer whatever we've developed or learned to be able to grasp trees or logs. So the first project was done again by Vincent Grondin, and the idea was to detect in images the location of where should we grab a tree with a feller buncher to be able to execute an autonomous cut. And again, he collected a bunch of data. Also, he created a simulator to get a first bunch of labeled data to pre-train the network, and then he fine-tuned it on about 100 real images. And you can see here some of the results. So yeah, not only we are doing the prediction of the pixels that belong to a single trunk, but also we're predicting these blue points, which are what's called key points. So the key point here would correspond roughly to where you would push the blade of a filler buncher. So it's located not too far from the ground. And it's important because in Quebec, if the stump is more than 15 centimeters tall, operators will get fined because they're leaving fiber on the ground. And of course, we're trying to be efficient with the fiber, the resource, so we don't want to leave too much fiber behind. You see those points here? These would correspond essentially to the diameter of the tree at the base. And the points along the tree would give you an indication of what is the orientation of the trunk. So he trained a simple mask RCNN network. And then you can see in the video here, I'll stop here because sometimes it will zoom. So you can see that most of the time we're able to see to detect all the trees which are in proximity of the machine. So the tree here was potentially not detected because it was too far, and we only label the trees which are close to the machine. Keep going the video. I'll stop here. So you see again, it does pretty good job, but you can see here some of the mask here leaked to that small tree here. So of course it's deep learning. It's learning. It's not perfect. Like here it missed a bit of the base, but generally our results were pretty good. And with modern hardware, we get about 5 frames per second, and that was 2 years ago. So nowadays, probably you can get 10 frames per second. That's really something that you can essentially demonstrate that you can use cameras in the process of automating tree felling. Another operation that we looked was grasping logs, which is a very common job in forestry because you grasp log. Once they're cut on the ground, you grab them to put them on the forwarder. Then the forwarder puts them on the side of the road. Then from the side of the road, you load them on the truck. So you touch log essentially 7 or 8 times before it is being turned into wood planks, for instance. So a very important operation in forestry. Again, we're going to be using machine learning, so we need data sets. So here we have produced what's called TimberSec 1.0. And an important aspect of data sets is you have to capture information in relevant environments. So we took some pictures from trailers and we labeled the logs which are at the top. Same thing for the roadside. You see we labeled logs which were at the top of the pile, which are close to the forwarder. On the wood yard, same thing. We labeled the logs which are at the top. And finally in the forests, we had dash cams that we have installed in tree fellers. So we were able to hunt down automatically for images that contain a certain number of logs. And then we basically labeled the challenging one. You see here, you have logs in all directions. You have this yellow log here, which is in 3 pieces in pixel space. It's a single log, but it's been occluded at different location. And in total, we have 220 images and labeled about 2,500 logs for this project. And we used a novel network at the time. It was called Mask2Former. And you can see the video here is stopped, but you can see that it does a very good job at detecting logs regardless of the orientation, because that's one of the issues is most detection pipelines that are out there, usually they expect your objects to be rectangular and access the lines, so either vertical or horizontal. And in the case of logs, the logs can happen to be in any orientation, and that is very challenging for, I would say, classical detection networks. But Mask2Former, because it predicts masks, it does a really good job at it. So we'll play the video here. I'll stop it a few times. So you can see that most of the time, the logs which has been detected is quite persistent. And you see that as I move forward, logs which are getting closer and closer eventually gets detected. Again, it's because we choose to label only logs which are nearby the forwarder. The reason is because the forwarder is interested in grabbing it with its grapple, and there's no point detecting a log which is 50 meters away if it's outside of the reach of the boom. We also were able to demonstrate with our commercial partner FP Innovation a demonstration of autonomous tree picking. So they have instrumented a small forwarder. So you see here the grapple, and there's a camera installed here, stereo camera, and here you have the digital twin, which is a 3D reconstruction frame by frame. So it's not a stable 3D map, but it's a reconstruction of the world. And at the top here, that's the view from the RGB camera, and you see that we are able to detect the log. Obviously, this is a bit of a simpler environment because we have a uniform background. It's asphalt. But nonetheless, they were able to demonstrate with us that you can do autonomous log grasping. And then you see here the log being dropped inside the basket. And the only operation that was done by a human was simply to tap on the screen to indicate which of the logs which have been detected should be picked up by the system. Yeah, so we'll see here a little bit how we can detect essentially all the logs in an image. I think we can do up to 200 detections per image. Another important operation in forestry is to what's called forwarding. So taking the logs that have been placed on the ground and bring them to the side of the road. And for this aspect, we wanted to exploit an algorithm called teach to repeat. So we looked at a problem, the definition problem in itself. So when you do tree harvesting, you essentially have a machine that will go around and will cut the trees. So if you equip the tree feller with a 3D system, then you can build a 3D map of the environment as you go. And as you cut the logs, you can record the 3D location of every single log which has been cut. And what's important here is the navigation. One of the difficult part in doing autonomous navigation is to detect is the ground traversable or not. But in this case, you can imagine that this harvester, it's a human who operates it. So the human makes the decision where the harvester can go and traverse the ground, and we will record the trajectory in the 3D map of the harvester, so we know that this path is traversable. So in a way, it's like we are laying down in the world a invisible rail. So that's the blue line here, and the forwarder simply will be like a train. We will put the train on that tramway. We'll put the tramway on the rail, and therefore our forwarder can autonomously go and navigate all the blue lines because we know it's traversable and we know it's been mapped with the 3D mapper of the harvester. And we also know that all the logs are located nearby that rail because that's the harvester who built that rail. So that's the idea. And we've done initial tests about 8 years ago. And you can see in the video here, if it gets a little, stop it here. If it looks a little bit blurry, it's because we have superimposed 2 videos. So we did the teach, the robot was manually driven by the human, and then the repeat. So you see here the 2 copies of the human, and then we repeated, and we see that the two instances of the robots are almost perfectly aligned. We get about an error of 2 centimeters in the forest. I'll continue the video here. So you see sometimes it gets a little bit blurry. And that's simply because of the error in relocalization. But overall, very, very effective algorithm. And my colleague François Pomerleau, he pushed that with a much bigger robot and for much larger distances. So they did experiments during 1 week where they first did the repeat part, the teach part, and you can see here the 3D map once in a while. And then you have also the view from the drone. And then they repeated over a week. They did about 20 repeats of the same trajectories, and they only encountered 1 failure case. And in total, they were able to traverse 20 kilometers of terrain that way. And that's with nighttime, also wind, snow, rain. We get essentially all weather conditions within a week. So it was pretty amazing for that. But one thing I think is important for the future of forestry is to start putting data gathering equipment on existing forestry equipments. Like here you have a LiDAR, the HAP LiveVox, which is like a frontal view LiDAR with a 128 beam density. And you have cameras here and IMUs, so that we can start collecting a large amount of data in an opportunistic manner, because people are cutting trees all the time. Might as well mount sensors and start collecting the information. And then we can do projects, for instance, 3D, can we build 3D maps from these scans that we obtain? If the answer is yes, then we can start building huge 3D models of forests, because if I play the tape backward, the machine is not cutting trees, it's planting trees. So I can build the complete forest as it was before it was cut, or I can rebuild the forest. I can rebuild the environments after the forest was cut, and so on and so forth. So there's a lot of research opportunities, but also doing more projects about automation of tree felling, because you can apply imitation learning. We will have like hundreds of hours of both 2D, so the images here, and 3D synchronized, all time synchronized, and start doing speeding up the learning of autonomous tree felling simply by doing imitation. So that was the first part of my presentation. The second part is more about the lessons we've learned, which I think it's very important. The first one is when you do machine learning projects, data diversity is key. Neural networks tend not to generate so well if you have small training sets. For instance, for the log grasping problem, we use images coming from YouTube. We also used images that were taken during the daytime, images that were taken at nighttime from the dash cams installed on tree fellers, and also images that were taken during the winter, because clearly the log you see here, the logs are covered with snow. So the network will essentially rely on that little thin dark line, and we're able to extrapolate where the rest of the log is based on the shape of the snow. So it's important to collect really data in all conditions. Second lesson learned was that the network architecture matters. I briefly hinted earlier that we use Mass2Former for log detection, so I'll stop the video here. The reason is it can detect logs in any orientation. The traditional mask RCNN does mostly axis-aligned object detections. So you can see here, for instance, it struggles with objects which are diagonal. Like this one here, it's not detected, and this one is. It prefers, for instance, horizontal logs. And then you have people like, that's 2015. 2017, you have rotated mask RCNN, which was designed to find boats, which are long objects from overhead images. So it worked better than mask RCNN. You see here the logs are crisper and you have less problems finding the diagonal logs. But clearly Mass2Former is a more generic shape detector, and it gave much better results. Lesson number 3 is you will have a diminishing return on data. So more data is better, more labeled data is always better, but it's not a linear relationship. So here you see 3 things we were trying to predict in images. That was for the standing tree trunk detection. So key points, bounding box, and segmentation. It's not really relevant here. What's important to see here is our metric of that we're interested is precision. Higher is better. And what we can see is obviously as we increase the number of labeled images, the metrics go up for all of these categories here of tasks. But pay attention here, this is a log scale, and you more or less have a linear relationship here in log scale. So that's what's called the power law. And essentially for our problem, we'll gain about 2% every time we double our training data set, which at first it's not so bad, but eventually it becomes very, very expensive. And that's why if you look at companies like Tesla, they might have a team of 30 to 40 research engineers, and they will have a team of 500 to 1,000 annotators, because they're trying to push the scale in terms of how much data they're using. So keep that in mind, because it's one of the first questions people have is how much data do I need for my project? Lesson 4, we labeled actionable items. Okay, the first questions we get when we start a project and we look at pictures that we start annotate is like, yes, but which object are we supposed to annotate? Because you look at the image here, if you put your head that you say you want to find the logs, then you will start annotating all these logs. But at the end of the day, our project is about grasping logs. So we chose to only label actionable items. So that way, the network will essentially ignore all the logs which are not graspable. So it's good, but also it will reduce the time we need to annotate everything. Lesson 5, no one wants to annotate. Okay. When you start a project again, you have to recruit people and to tell them to annotate, and then they refuse. They don't want to do it. It's too boring, and so on and so forth. And I think the perfect analogy is tree planting. It's nobody wants to do tree planting because it's a boring task, very repetitive, and you do one action, which is push something in the ground. Well, data annotation is the same thing. You go on the screen and you click. And just to give you an idea, this is the video made by Jean-Michel. And you can see here he is trying to do a polygon that will cover entirely one log. And it took him 44 seconds to label one log. And we have 2,500 of those logs. So it's very tedious, but so important to do. Lesson 6 is tech transfer tend to be quite slow in the forestry. So maybe we should focus on what's called proximity innovation, where we try to add value without changing current practices. And an idea, a good word for that was Sanjeev Singh that gave a good presentation at a workshop on field robotics that says, people right now on AI, they focus on jet fighters and toys when it comes to field robotics and automation, because these are jet fighters because its military has a good appetite for risk, and toys because people who are enthusiastic about technology are willing to tolerate failures. Sensor placement is key in robotics, but it's hardly compatible with forestry equipment. So you have things like we have to place camera behind metal bars to protect them against incoming logs when you do forwardings. But you look at self-driving cars, we place our sensors on top of the car. But if you do forestry, if you place your sensor on top, well, your sensors will be gone after a few trees being cut because this is so common. So you have to build robots that are able to withstand being hit by a baseball bat of 30 feet long. So that's what we have to do. Lesson 8, there's not a lot of roboticists which are working on forestry things. Today, you're lucky we're 3 of us. But to give you an idea, at ICRA conference this year in Japan, there was about 2,000 papers and less than 5 tackled forestry problems. Last lesson learned, 3D mapping can be fragile. So beware that when you buy a commercial like 3D SLAM solutions, they tend to be targeting structured environments like urban areas. And LiDAR SLAMs loves flat surfaces and corners, and you don't find a lot of those in forests. So beware of that. So there's many parameters to tune. It might be very difficult. And we at the NOR Lab developed our own 3D pipeline for creating maps. It's called Leap Point Matcher. And we still find it hard sometimes to build maps in forests. So to conclude, robotics and computer vision, I think, offers many solutions for the forestry industry and researchers. We have SLAMs, we can build 3D maps, inventories, and navigation, but also deep learning, can do species classification, log tree detections. But the progress has been slow so far. I think it's because of lack of data sets. That's why we publish a lot of data sets on our side. And also, very few researchers are doing it right now. So, but I think it's a bright future. All right, that concludes my presentation.
Awesome. Thank you so much, Philippe. And it's a wonderful speech. You present a lot of innovative studies ongoing in your lab. And I really like the lessons you gave in the end, especially lesson 6, since I know like forestry is always for a little bit behind than other industries in technological innovations. And yeah, so it's really hard to really implement some innovative technologies in this industry to improve productivity, for example. But that's a long path we all need to work on. And I saw someone put his or her hand up. Would you like to ask any questions? Anyone raised his or her hand before? And I didn't see anyone post any questions yet. So actually, I have just one question. So how much time and you have spent you and your team has spent on the annotation part, and did you pay a little bit for the annotators?
We didn't pay for annotators. I feel that that you get what you pay for, and when you hire annotators, these are people that will be paid like dollars per hour,
Mm.
dollars per day sometimes.
Yeah.
So and the other thing is when you annotate, when the students or researchers annotate the data, is you start understanding your data because you see
Mm.
it, you understand the edge cases, and then also you might get ideas. Oh, okay, I didn't think about that. Maybe I should do this with my network,
Mm.
or I should use this and that. So I feel it's a
Mm.
way of also spending time thinking about your problem.
Mm.
But of course, when you, and also I feel that, because we're of this power law, I was surprised that sometimes with 100 images and thousands, a few thousand of instances, it's enough to do a project. And I
Mm.
think that's where academia is good at, is we do the proof of concept and we get, I don't know, like 65% precision,
Mm.
because we know that to go from 65 to 80 is just a
Mm.
matter of throwing more dollars at the problem.
Yeah.
And the companies won't throw the dollars at it if they don't have a demonstration.
Mm.
So that's what we do. And then once they see it works, then it's just a matter of doing the engineering.
Mm.
Uh, and they have the pockets, then they can go and pay for the annotation.
Yeah. The training data is really important for this game, and
Yeah.
I really appreciate you published all your data sets on the GitHub for public use, and
Thank you.
a lot of that's very beneficial for this whole community now and in the future.
Yes. Thank
And
you.
yeah, I got a lot of questions right now, and so let me pick um one first. So for the bark identification, how does this perform for younger trees or trees with low branches? Does this function in these circumstances, or a different solution needed?
No, it does. It does work for any age, and it's very important because one of the things we notice is you have a lot of intra-class variation in appearance. Like for instance, the maple, when it's very young, it's very smooth surface, and when it's old, it's there's a lot of cracks and crevices. So it's a question of data sets. If you have to make sure that when you collect maple images, you have to collect young, medium, and old aged trees. If you just collect young trees or old trees, then when you're going to present, if you only have old trees in your data set for maples, then most likely your maple tree will be considered as, I don't know what's the English term for these trees with smooth bark. I think maybe ashes. Like they'll be classified as that. But
Mm.
being young, or of course, if it's very very young, like maybe less than 2 years or 3 years, yeah, the bark is not. You would have to be very very close with your cell phone. But then in that situation, I think it's better to rely on the foliage. And I would say from a commercial point of view, because you will not harvest those trees anyway, then unless you go do inventories in the winter, then you will be able to have the leaves. But for the bark, I guess one of the take-home messages for commercial applications, sometimes the leaves are very up. When you're in the forest, the leaves are up in the sky because there's no sunlight enough low. So you need to be able to see to use the bark to do the species identification. And also when you do the logs, then you don't have access to the leaves anymore.
Okay, thanks. So guys, I got many questions from my direct messages. So please post your questions using the Q&A function. If you can't find it, you can maybe click the more button and find it. Once you posted your questions on that, Philippe can answer them after his presentation. And so let me ask one more question. So have you seen any research focused on the tree planting stage rather than logging?
Tree planting, good. We're trying to go there.
Mhm.
And I talked to a researcher a few weeks ago, where so there's this company called PlantMax that does I think the company is called PlantMax, or the project is called PlantMax, where they have this machine, two arms that goes in plant trees. And the researcher at Skopforsk, they basically use cameras just to look at the ground right before you're planting a tree, just to see if it's a rock or not. And so to basically increase the chance of success that the plantation would be effective. But I think it's just starting. Like I think it's a good area to actually start doing research, because yeah, people have focused on harvesting first. It's still not done. Trust me, there's a lot of work to be done in harvesting, but I think tree planting is a good area. But there is challenges, like when you cut trees. Yeah, the machine weighs several tons, and you know that the machine is built to traverse the terrain. But when you do tree planting, typically it's done by humans. So the set of the machine that will go plant the tree might be smaller, which means traversability issues might happen. But maybe then again, people will just use giant drone to go and stick trees in the ground. I don't know. But yeah, I hope to start doing research in about 2 years on that topic.
Okay, awesome. So let's skip to the next presentation, and Philippe, you can just answer the questions posted in the Q&A section. There are many of them.
Excellent.
Yeah, thanks. Got it. So yeah, give me a second. Let's welcome Dr. Wu, and he's an assistant professor of advanced forestry system at the College of Forestry at Oregon State University in the US. Today, his speech topic is current and planned research in advanced forestry system, robotics, and LiDAR applications in forestry. Doctor, would you like to share your screen with us and start your speech?
All right.
Yeah.
Can you see the screen?
Yeah.
Perfect. All right. Thanks for the invitation for this conference, and I'm really excited because this is kind of topic is very interesting, and currently the interesting about the robotic application and sensor application in forestry is dramatically increased. So I'm more than happy to participate this kind of webinar, and I hope we can make more chance to join this kind of meeting to discuss about our like current research topic and advanced forestry technology. Today's my topic is I want to share with my current research with you guys. And as Worters introduced me, I'm a new professor in Oregon State University. I teach in advanced forestry system. So yeah, great to see you again, guys, in here. Okay, so I'll just briefly introduce by myself for you guys, and introduce the research just briefly. So my name is Heesung Woo, and I actually came from the South Korea. And I think I met Philip and the other guys, and most of the robotics and advanced forestry is run by like a mechanical engineering. So I briefly introduce myself. My name is Heesung Woo, and I'm the guy who got a background in the forestry mostly. So I got a bachelor study in forestry in South Korea, and after that, I got a first master in South Korea related in forest management. After that, I moved into the United States for my second master in the forest engineering. After that, I moved to Australia for my PhD in the information technology. And at that time, I was studying for the, computer science and how can I using the advanced technology in the forestry. So this is my background. So I'm not a robotic like hardcore person. So I might be can share with you more like a forestry perspective for my research. All right, so you can see this picture of the left side and the top of the picture. It was taken by the 19th century and around the 1800 years. They are using the like a caliper to measuring the tree DBH. But right now in 2024, we are still learning how to using the DBH, how to measure the tree DBH using the caliper. And also, the chainsaw was, invented 1830, but we are still using the chainsaw as a, main tool when we are cutting the, tree, especially in hand felling. But in 1977, United States, they John Deere, they are starting to manufacture to produce the harvester machine, which is harvester machine is originally developed by in Finland country, but the USA, they are starting to manufacture this machine to tree harvester. So after this is kind of the historically about the technology advance in forestry. So we are now talking about the 2024, and today's topic is what's going on in the industry 4.0 in forestry sector. We have a couple of challenging right now in forestry. First of all, is aging forestry worker, which means there is lots of forestry people and workers are getting old. This is not only for the U.S. Came from the South Korea. South Korea has way more extreme case. So most of the forest worker in South Korea is more than 50 years old. So they are really, old. That is a really big problem. And also there is a reducing and decreasing forest employees from the young generation. So as an industry, and not only for that, also academic, there is a less interesting about the young generation. They want to study forestry, field. So this is one of the big issue. And also there is a required convergence of AI, robotics, and ice techniques in forestry. So we are really interested about this kind of technology to improve this kind of our face challenge. So based on the McKinsey report in 2018, they said precision forestry can be the key to solving this kind of the issue. So based on the precision forestry and advanced forestry and smart forestry, there is lots of terminology to call about the advanced forestry technology. So you can see this kind of the figure. There is lots of increase from the 2005, and there is lots of people are starting to using the drones and the TRS system to starting the forestry, and they are starting to application for this kind of technology in forestry section. However, there is a critical problem to use this kind of technology as a forestry perspective. We know radar is very great tool for using forestry, but the price of this kind of system is really expensive. So small scale forest landowner are very high, very limited to access this kind of precision level of the data and this kind of technology. You can see that the price range of the radar sensor. This is proprietary system which is manufactured by the company. And if you are using the radar system in the forestry, you have to purchase this amount of money. I know the speed of the development technology is very fast, so the price will be decreased in the future. But right now we have still this kind of problem. Because of that reason, I am really interested about the real implication about the radar technology in the forestry. So I'm starting to developing low cost radar system in forestry application. So compared to the last presentation, there was very high range of the price of the radar system. But if we are built by ourselves, the hardware cost is just less than 100,000, 10,000 K. So way cheaper than purchase like a proprietary product. But the key is, as Philippe mentioned before, the key is a SLAM algorithm. If you have a poor SLAM algorithm, you can get a very poor result. But if you have a real good SLAM algorithm, you can get a pretty good result for the 3D mapping solution. So I developed this. This is like one of the prototypes. So we are using the 32 channel about the radar sensor and using the single board computer from the NUC and using some display and monopod. And the SLAM algorithm is developed by the Kudan, which is my collaborate company, and they are focused on developing the 3D SLAM algorithm. So we're testing in the real field, and the result is pretty good. So this is out of the low cost system of the radar. And when you extracting the LiDAR data from this kind of point cloud, you can get a actual DBH information from the LiDAR system. So we compare to the ground truth data with the we apply the number of the sector fitting algorithm and figure out which algorithm is the best suitable to estimate the DBH. However, there is some limitation. When we exporting the SLAM algorithm, SLAM output, we have some distortion, especially in the Z value information. So there is lots of still challenging to improving the like a industry grade application in local systems. So we are still working with our industry partner like Kudan, and we are working more to improving this kind of result. Second one is we have a low cost LiDAR system. We want to put this one to the robot. So this is so I mentioned before, my background is forestry. I have no background in robotic before. So this is the like approach I did as a forestry background person. How can I implementation of a robotic in forestry? So the reason I interesting about the using unmanned ground vehicle instead of the UAV we is when you collecting the if we are using aerial laser system, that is really efficiency to cover the large land area to capturing the LiDAR information. However, there is a very critical limitation to gathering under canopy information. So if you are using very high expensive sensor like a legal or like a very expensive sensor, then you can get some kind of very small amount of the some under canopy information. But if you collecting very high precision level of the under canopy information, you need to go inside instead of the flying the drone. For example, but especially I developed this machine in South Korea. The South Korea, the forest condition is very dense. So the crown is really dense. So it is really impossible to capturing the data from on the canopy using the drone. So because of the reason I developed the unmanned ground vehicle. So this is the first time I tried to make a robot. This is not a robot. This is kind of a toy because I have no budget to purchase the robot platform because the robot platform is really expensive to purchase as a researcher. So I just purchased some kind of RC car and put some sensor on it and make with a suggestion TX board to trying to understand the communication with the sensor and the robot platform and the computer to gathering some information using the robot. However, this is so from this kind of application, we found some outcome. So at the time I don't have any budget to purchasing the LiDAR sensor. So we are using the stereo camera and trying to using the BlizzSlam algorithm to gathering some 3D point cloud information. But it takes a lot of time compared to the LiDAR application. So it is so if you are using the if you want to apply in the forest inventory analysis for the 3D point cloud mapping, it is not a good solution. And there is also a network error between the robot and control PC. And especially the platform of the robot is really small. So it is impossible to actually access to the real forest. So this is like my outcome from my first time. So based on this kind of my experience, I writing a research grant in Korea Forest, Korean National Research Foundation, and I got some grants to purchasing this kind of more big size of platform of the robot. So I put like a rear LiDAR sensor on it and IMU and stereo camera and make it and this is like a configuration of the prototype 2 about the multifunctional vehicle. So this is actually testing in the indoor, like in my lab, we are testing to create the 3-point cloud mapping using the SLAM algorithm SLAM, and the result was pretty good. So I just keep it here. So indoor condition, it works perfect because there is lots of corner edge and there is like architecture stuff. So it is really easy to capturing the data with a precise level. And I tried to climb up to the stair. The manufacturer said it is available to climb up the stair, but I put this LiDAR sensor on the top of the machine. So if the rollover issue, it must be breakdown. So I might be losing the one of my sensors. So I try that, but I can't actually test in the field. So this is a result of the indoor mapping, 3D mapping. So we can get a pretty good result. But when we're testing the outside, so I bring this robot to the outside and before we go into the real forest side, and this is kind of real situation. It is really risky because if you roll over the robot, you can easily lose the the LiDAR sensor. The expensive part is the LiDAR sensor. The LiDAR sensor right now is of course is very it is reasonable price than previously, but at the time it was really expensive. So because of that reason, I put some, the protector bar in here before we heading up to the field. So we are drawing the older, this the uh, prototype as a like a scanning. So we did some aluminum profile and put some like a high spec of the computer. And we figured out, I discussed with some like expert from the robotic people, and we found the location of the sensor and the make the center of gravity more stable. So after that, we are bringing to the field to select to test in the application. So here is the the actual test in the field. So it has an autonomous function. So the robot is moving in the forest, and the right side of the video you can get a extra data from the SLAM algorithm. So this is real time street mapping. So it works pretty well, but I can't say that this is the result is not a great. We have still lots of problem because there is a slippery issue and also the soil condition is really highly impact for the robot movement. So the size of the robot is pretty not enough to climb up to the in real forest, not only forest road, in real forest, actual field side. So it has lots of limitation, but we have a really good output and run from this kind of trial. And after that, we are the gathering the 3-point cloud information is not enough. That's not a the end of the journey. If you have a 3-point cloud data, you have to using as a end user perspective, there is some kind of solution for like a automatic segmentation for the tree stump, tree crown, and that kind of information. But the forestry people and especially in the industry perspective, there is no many people are using the computer science technology to using the AI deep learning to to learning like the 3-point cloud data to get us what they want on what they really require their information. So because of that reason, I developing developing point snap approach plus tree segmentation algorithm using LiDAR data set. But you can see the result in here, like 5 verification error accuracy, the result. The result is not great because there is lots of it requires a lot of training data, and the tree condition about the forest condition in forest is very dense, and the tree shape is very shanky. So it is really difficult to figure out the segmenting the tree stump and the tree crown. but we still gathering the leveling all the data, and there is lots of time to do this kind of to improve these kinds of result. So right now I just moved from the South Korea to here, so I'm just find some graduate student to continuously work to developing and improving this kind of result. So so this is my last research. So sorry, there is some like a delay for my presentation, so I might be passing maybe to five or three more minutes to presentation my topic. So right now we have a 3D SLAM algorithm, and we know how to communicate like a robot and the sensor and computer. So the question is, so there is lots of option for the LiDAR sensor, but if we don't have an understanding about the LiDAR SLAM algorithm, there is no actual application LiDAR sensor in forestry. But we have we are working with the Kudan, and we have a pretty good SLAM algorithm in forestry application. Right now, we have a question: which sensor is enough to collecting the forest inventory data? Because the price range of the sensor is really really various. If you are using the very reasonable sensor, you can purchase like $2,000, something like that. If you purchase a 128 channel like high resolution sensor, it costs a lot. And also, we don't need that kind of high resolution sensor, because if you're processing that kind of high resolution sensor data, it needs lots of computing power. So there is not that. So that kind of thing is, I think, it is not applicable right this stage. So I want to investigate which sensor is enough to apply in forestry. So I'm now testing a number of sensor like a Hostai and Ouster and Barodyne and also Rivals. So we are just attacked to, you are just equip the sensor with the same condition and using the same apply with the same SLAM algorithm to figure out which sensor is enough to gather our targeted information. So that is now testing for my short. This is my current research right now. So we are now testing. This is like a prototype of the the machine configuration. So we developing the user interface, and you can see actually the data as a real time to the focusing on their lidar sensor and the stereo camera. So this is the result, and also I'm doing the real time colorization point cloud data with the stereo camera information, but that there is something like a distortion limitation, distortion error. So we are trying to figure out improving the output of this kind of street point cloud data. So yeah, this is my current work, and right now is I'm the special I'm the specialist guest editor for the cutting edge solution in advanced forestry into the sensor AI and IoT robotic and connectivity. The topics in Forestry Journal. So I want to introduce this kind. I'm more than happy to you guys have any interesting to apply any like a research article. Please please welcome to submit this special issue. And this is my final, slide. And our view will be changed from the, upside of picture to the, bottom side. And thank you.
Thank you so much, Dr. Wu, for your presentation and any questions. And I saw you really pay a lot of effort to reduce and control the cost of your studies, and the funding is always the biggest limitation in academia.
Yep, exactly.
So, I'm curious about like what kind of funding you're applying for. Maybe you can apply robotics, help you to study more about robotic applications in forestry and the forest sector.
That's a really good question. So right now I'm looking for the NFA from like a NFS funding in United States, but so I just moved into the United States 6 months ago.
Yeah.
So I'm not a familiar for the all the grant system in here, but I try to, figure out the good funding, maybe USDA, NIFA, and also NFA, and also there is also NASA. So I'm looking for any chance of, like a funding opportunity right now. All this kind of machine and the research was conducted in South Korea from the South Korean funding, but in here I'm still looking for the any good funding opportunity. Maybe this year and next year I might be apply, yeah, some of
Okay.
the proposal for
Okay.
continuously working for this project.
Okay. Here's one question from Matthew from SNRC, and he asked, what made you choose a land-based robot over a under canopy flying drone?
Under canopy flying drone, I have this under canopy flying drone. Actually, the Australia company MSN, they have the technology to the autonomous flying drone. So I have the hover map, which is called the hover map system. So already have it, but it is impossible to actually in the forest in the flying in the real forest. You can fly in the some kind of plantation, but there is lots internationally in South Korea, in Asia, and and Brazil, and lots of countries. They have tons of different like environment. So if you are want to apply in the like that kind of real forest, I think there is a lot of limitation for the flying drone on the canopy, but I'm pretty sure I'm when I have a free time, I'm watching the like a movie. So when you see the movie like what is the name of the Prometheus? Do you see the Prometheus movie? They are flying just the small ball and they're scanning all the system, all the the 3 point cloud in the cave. In near future, I'm pretty sure in near future it must be happen. But right now, I think the flying drone is yeah, because we have drone is not a problem. We have a problem. We have a limitation for we have a challenge for the battery. We have a challenge for the uh what's the weighting of the sensor. So that kind of has to be solving the simultaneously. So I think the ground is more easily controlled to the flying drone. And I have some kind of phobia to flying drone because if we are losing control about the the drone, it is easily just falling down somewhere, and the price of the the equipment like the sensor and all the computer is really expensive. Yeah, so.
Yeah. Okay, got it. Thanks for sharing. And we still have some questions in the Q&A section. You can just answer them after your part. And feel free to put your questions for Dr. Wu on the Q&A section. So we need to move quickly and to welcome our next speaker, Dr. Mattamala, to present his research at Oxford Robotic Institute. He's a postdoc researcher there, and he used to be a PhD student there. And the topic is about developing robotic technologies for sustainable forestry, and specific about the DG Forest project, which is part of EO Horizon project, right? Yeah. Okay, got it.
Can I start now? Okay, all good. Yeah, thank you very much for the invitation. So in this talk, I want to talk about the forest project that Walter presented like quite nicely. So I'm going to cover different aspects of the project because it's an European project. So it's 3.5 years in which we're developing many different things. So I'll try to do my best to cover all the aspects of it so you can have a very good overview of the research we're doing in this context. So, but first of all, I would like to give you some personal background overview. So yeah, so as Walter mentioned, I'm a postdoctoral researcher before I did my PhD here in the University of Oxford. So my background is in robotics, so it's not in forestry. So I got involved in this problem just like a few years ago by the end of my PhD when I was working on navigation of robots in different environments, because my main research interests are in how to make robots move from A to B. Basically all that requires like all the fundamentals, algorithm systems, how to implement the systems and how to apply to different problems, in this case, forestry. So most of my research so far has been like deploying and developing a navigation system for quadruped robots, as the ones that you can see on the picture. And I will show you a few more examples later in the presentation. So in this talk, I want to talk about the Bee Forest project that I will introduce in a second. So mainly the vision overview, what are the partners involved if you are interested in learning more about the project, the vision of the project, and some of the robotic technologies that we're developing as part of it. And I will finalize with some conclusions and maybe leading towards the panel session. So first of all, let's start with the forest. So the motivation for the forest of this EU project is that 43% of the EU is covered by forests or woodlands, and we want the good production to be more environmentally kind of aware. So we don't want to do clear cuts. We want to do selective cutting and kind of do more precision forestry, as Heesung was mentioning before. We want to minimize the soil impact. So there are all these aspects that are related to how we do forestry that we want to kind of address somehow in this project. And on the other hand, we also need more data because we want to improve the decision making. We want to do like this precision forestry. We really need to know like fine-grained information about the trees. And for that, for example, the main technique that we use in this case is ALS, so airborne laser scanning, right? So, but the problem is that it's really coarse sometimes, and you don't have information about what happens under the canopy. So these are some of the aspects that we want to cover in the project. So the Forest project is trying to address this problem. So it's a Horizon Europe project. So it's 3.5 years. It started in September 2022. And the goal is to develop robotic technologies to achieve this sustainable forestry, in this case, like precision forestry, how was introduced before. So the consortium is quite big. So we have different partners all across Europe. So we have Munich, we have this technological university in Norway, Bonn. We have other companies as well, ETH Zurich, WSL, that is a forest landscape snow research institute in Switzerland. We have companies as Hexagon, and here there's a mistake here. It should be Pre4, that is, they changed names now, MOOC, and also other partners from other institutions. Okay, now it looks good. Yeah, okay, so and the ambitions are the following. So what we want to do in the project is that we want to have a team of heterogeneous robot platforms. So different like drones, we want to have leg robots, we want to have wheel robots, that basically they're going to map the environment and going to provide fine-grained tree-level forest data. And in order to gather this data, that it can be input to a decision support system that's going to allow us to do informed decision-making and then do autonomous tree cutting, right? So we have this whole pipeline that we're trying to address in the project, and I'm going to cover some of these aspects one by one. So let's start here with the autonomous robots part. So all about the platforms. So let's start with this. So, okay, we have the forest, and these are all the platforms that are involved in the project that we're developing like in all these different directions. So first we have over canopy platforms. So for example, this drone that is teleoperated, that is going to map the environment from above, right? So it's going to have aerial laser scanning, and it's going to provide like a pretty good overview of a large area, but from above the canopy. On the other hand, we're going to have several under canopy platforms. So for example, we have some drones that are developed by our partners in Norway. We have some industry solutions like the Leica VLK to fly drone. And we also have some legged platforms like the Anybotics animal robot that you can see here, like the red robot. And also we have some device that I will talk about a bit later, that is this Frontier device that is like a custom built mapping solution. And lastly, we have this harvesting machine that is called Harvery. I will also explain a bit more later, but it's basically a lightweight solution to go and kind of cut the trees, minimizing soil impact, because other machines are quite big. And one of the concerns that we are presenting in the project is that we don't want to kind of compress the soil or kind of destroy everything around. We want to have a pretty lightweight solution. Right, so I will cover this briefly because this is not the main line of work that we're developing in Oxford, but it's really important because it's about our other partners. So one of the areas that we're developing is all about navigation in forests with drones. So for example, one of the challenges that Heesung was mentioning before is that drones really struggle to navigate in real forests. So for example, we have two teams in Norway and also Munich developing new navigation systems to enable drones to navigate using LiDAR and also vision. So that's one important line of work. I will put all the papers down there, so if you have like any questions or want to refer to them later, you can check the slides and you will find them there. So now more on the Oxford side, that is what we're developing. So we have the solution that we call Frontier, that is a custom-built device that we use for online LiDAR slams, so basically localization and mapping. So here's like an example of the kind of signals that we obtain from the sensor. So we have some online cameras, and so we have 3 cameras, we have a laser, we also have some online computing, we have GPS measurements, so we have everything like nicely packed. So we use it like for different applications. And for example, we use this device both for backpack-based mobile laser scanning, as you can see on the left-hand side, but we also use it on our legged platforms as a payload, as you see on the right-hand side. And this is like the main component that we use for some of the research that we do here in Oxford. And it's also being used by some of our other partners that we have in the project. So in this part, so one of my areas of research is about deploying these legged platforms that I mentioned in the previous slide in the forest to collect this data for us autonomously. That is really like a robotics problem, right? So it's related also to what Philippe was saying before. So in this case, we're deploying these legged platforms because they have certain advantages compared to, for example, wheeled ones. Like they will basically be able to sort out like different obstacles. They will negotiate obstacles like different terrain, and they will be able to navigate like in the environment in a more kind of dynamic way. So, for example, one line of work that is the one that I'm specifically involved in is about deploying this robot to collect the data for us autonomously. So this is one example that we did in this deployment in Finland in one of the field trials of the project. And in this case, we deployed the robot to collect data. I think it was maybe a plot that was half a hectare or so, and the robot was able to navigate in the environment and collect this map using SLAM techniques that we could process later and do more interesting things with it that we'll present in a bit. So once we have all these platforms that we're deploying in different ways, we're interested in mapping, right? So I showed briefly, I hinted how we do it with the legged robots. We used to do it with the drones. But the problem that we have in the project is that we have different platforms with different nature, right? So some of them are aerial, some of them are terrestrial, some of them is a backpack that somebody carries. The other one is an autonomous robot exploring the field. So we want to combine all of this to have like a joint map of the environment. So that's one of the challenges that we've been like addressing in the project. So for example, here, one of the technologies that we have developed is like multi-session mapping. So for example, we can make a map with the backpack and we can make another map with the legged robot, and we can combine these missions together and have like one combined map that basically will have more information because it's kind of aggregating the point clouds that were obtained by the backpack device, that, for example, in this case was 2 meters above the ground, while the legged robot is just 60 centimeters above the ground. And we can combine these together. And the green lines you see here are the trajectories of both devices that we can estimate from our SLAM system. And they're put together to build this kind of combined 3D map. So other problem as well is that we have drones that fly over the canopy, as I mentioned. So we have also investigated, we have one paper that's going to be presented in this robotic conference this year, in which we are combining aerial maps from the drone that flies over a canopy with sequences that are collected by the backpack mapping system. Like it's a person moving the sensor around. And we can also combine them and have like a more complete reconstruction of the environment that is useful to, for example, estimate traits like DBH, as Philippe was mentioning before, or other parameters that we're interested in, for example, the canopy volume or like the height of the tree or so. So for example, in some of this, in this research that we developed, we show that as expected, you get like a higher like density of points across, sorry, I had like a problem here. I cannot see the window. For example, for the different tree heights, we will be able to cover more of the space, more of the volume of the tree, because we're combining these two different sensor modalities. So this is other research that we have developed. And other of the applications of mapping that are also interesting is that, yeah, we have different platforms, we have aerial platforms, we have terrestrial platforms, but we also have information that we collect over time. So other of the technologies that we have developed is like systems to combine multi-sessions, being a session, one of these data collections done with one specific platform at one specific time. and we want to combine them like across different times. So for example, there is one test site that we have in Switzerland that we actually went there last week. But we also went there in March and in October last year. So we had data sets that are of the same places, but they are quite different because of the different seasons. And now we have a system that is also another paper that is going to be presenting in the same conference this year, in which we show how to combine these different missions collected at different times in a robust way, so we can build like one single combined map of the whole environment, including like all the changes in vegetation that we have. So here's like another view, for example, from March is green, October is blue, July is red. And you see that in March, for example, that was closer to the winter, everything was really kind of dry, right? So there wasn't that much undergrowth. But for example, when we went last week in July, it was really covered. So you can see all those details at a really fine level because of this pretty accurate multi-session mapping and multi-mission merging system we have. So moving on to the decision support systems. So I showed these pretty nice maps, right? So built from different platforms, from different, from the ground, from the air. But the next question is how we can extract meaningful traits that can be used to support the decision system that we need in forestry, right? So one of the methods that we have developed, we have explored similarly to Philippe, some tree trait estimation methods. In this case, we segment trees, different trees, or we also compare with different sensor modalities that is also aligned with what was presenting in the previous talk. So we have here on the left from this BLK2Go scanner that is like an industry solution. And there are other devices that, for example, the HESI32 is the one that we use in this backpack mapping. And the VLP16 is the one that we had available on the robot back then before we actually installed this payload as well. So this sensor payload. So in this work, for example, we analyzed how we could extract and segment trees, extract these traits as the DBH in an offline manner. And there is this paper that we presented this year in this another robotics conference, explaining all the challenges here. In Oxford, we were exploring some of these ideas before. The previous one was a work led by our colleagues in Bonn in collaboration with us. So we also explored some of these ideas a few years ago. This was in 2022, in which we were trying to estimate these traits online. So we developed a system that was able to, as the SLAM map was being built, we could segment trees and detect the DBH. But there were like some challenges here because the sensor setup was not ideal. And also the accuracy that we got was around 7 centimeters. But it was one of the first steps that we took here in our group in Oxford towards these applications. So now we have a new version of the system that is going to be presenting in another robotics conference this year that I'm going to show you now. So this is like a more sophisticated method that is really exploiting the fact that we are collecting a mission online. So as the robot is moving, it's collecting data and it's running a segmentation online, and we can estimate the parameters on the fly. And we, for example, can exploit information such as partial observability. For example, if the robot is on one side of the tree and then goes around and you can see the other side, then the estimate will improve. So we can refine these parameters as the robot or the platform of the backpack goes. And in these field trials that I was saying we had last week, we had a really nice application that I'm going to show you here. So here on the left, you will see the online reconstruction that the system that we developed is doing. So you will see in color, you see the tree segmented, and you also have in green the trajectory that the device is following. And on the right-hand side, we have a visualization of the system that is because this one is generated in post-processing, but this one on the right is something online that you can observe on a tablet as you're walking in the field. So the interesting thing we did is that we had one of our colleagues walking with this device and the tablet, and there was another person, a forester, like with the big caliper, measuring the trees, and we could confirm like in real time, basically how accurate the system was, and also how the estimates were improving as you were walking in the forest, because you will see here that all these circles that you see here on the right-hand side are basically the DBH. And after the person was moving in the forest, these estimates will improve. And we could confirm like directly using the caliper if the estimates were fine. And they were roughly less than 2 centimeters accuracy, and which was quite nice for us given that this was being shown online. So And the advantage of having this interface is that you could have direct feedback. For example, if one estimate was not really good, because some of the trees will be displayed in red, meaning that the estimate is not, we're not super confident about the estimate at this point. So you could kind of get this signal that could tell you maybe you should walk around the tree more times if you want to improve it, or there are like way more things that we have thought that you could do just by the fact of having this graphical interface giving you feedback. So on the robotic side, and related more to the work that I do, so we have been doing deployments to test the same pipeline to detect trees online, but in an autonomous fashion with the legged platform. So we have the same sensor payload, the same system, but this is integrated with an autonomous system that follows this kind of lawnmower pattern. So the robot will autonomously walk around and will collect the data instead of being somebody doing this process for you. So this is one snippet of a mission that we did here in the UK in the Forest of Dean, that is a forest near Wales. This was autonomously. They were like, at this point, we cannot just deploy the robot autonomously without supervision. So we always have a procedure in which somebody's kind of supervised and the robot's doing the right thing. But this is enabling us to kind of analyze the performance of the autonomy system as well and see how far we can push these platforms to perform this kind of task for us, right? So in this case, the road covered roughly 1 hectare. So I think the distance like across the longest area, the longest line was 120 meters. In total was maybe 60 roughly. And the robot finished this mission in around 20 minutes. So this was quite interesting also to see because it's kind of showing the potential that robots have to achieve these tasks. Lastly, in this space, we have also been exploring other that could be potentially interesting applications. So we have fairly robust localization systems. So that means that say that you have a map of the forest and then you revisit the map again and you want to know where you are. So we have a system to tell you where you are just using the sensor data, for example, the LiDAR or the images. In this case, it's just LiDAR based. And to show how accurate it was, we did like a render of the previous trees that we detected in a previous mission, and we revisited the place, and we kind of could show this kind of AR application in which we could kind of inspect the trees and the DBH of the trees. So you see here the live image, you have the render image on top, and you have the position and orientation of the person walking around in the forest. So we show this, for example, with the backpack system, and also with the legged robot, we could generate the same kind of visualization that could suggest like other interfaces that we could create to enable like a better and more easy inspection of the forest or kind of solving other tasks. So lastly, I think I'm around time. The last bit of the forest project aims to do harvesting, and we want to do it autonomously. So this is work mainly done by ETH Zurich with this other company called Pre4 in Finland. So they are focusing on this platform that is Harvard, but another Finnish company, because it's lightweight, because they want to minimize soil impact. And ETH and Pre4 are leading all the efforts to make it autonomous. So they've been like characterizing the machine, kind of checking how they can do control of the cutting arm, for example, and how to navigate with this harvester as well in the forest, because ideally this machine should exploit the maps collected by the other platforms. And then since we have the information about the trees, we could be able to say, I want to cut this specific tree, and the machine should be able to go and cut it directly without any human operating the machine. So here there are like some preliminary results by the team in Zurich, in which they're doing a navigation with this platform that also presents some interesting challenges from a robotics point of view, because it's articulated. So it's not like a rigid body, but it has like this joint in the middle. So there's some interesting challenges there in terms of navigation and collision avoidance. And particularly last week in this field trial in Switzerland that I mentioned previously, they were doing some initial experiments. So unfortunately, I cannot show cutting videos. There were like a few autonomous cuttings, but it's all preliminary results. But these are like some images to give you an idea of the setup. And the machine was like moving autonomously along this road, and it was kind of approaching some of these trees that we were allowed to cut, and having some initial results in this space. So to conclude, so yeah, the forest is like a big project. It's this European project, as I mentioned. It's 3.5 years, so we still have 1.5 years left to do more stuff. There are many directions, many research, many ideas happening. So stay tuned. I have like a link of all the research groups involved if you want to learn more about what we're doing. So this is covering like different aspects. So for example, from the robotics point of view, all these challenges about navigating in natural environments, collision avoidance, like traversability estimation, as Philippe mentioned before, and also all about extracting these traits and to improve the decision support system. So it's like a really kind of a big project covering all this, trying to cover all these aspects. And there are like still many research and application challenges, I think, that we can discuss maybe more in the panel. Like, for example, from the research point of view on the robotics side, I think that there are like many challenges about how to deploy these robots robustly and in a reliable way when we want them to do tasks autonomously for us. An application also, I think somebody was asking in the Q&A before about the technology transfer, how these technologies can be adopted by the forest industry. So there are many challenges that we can discuss further. But with this, I would like to conclude. So thank you very much. Here are like all the links to all the partners involved. If you want to learn more about them, we have all the links here. And if you have more questions, you can also ask me directly now or after the seminar. Thank you very much.
Thank you, Matías. That's a really awesome speech and including so many innovative research. And it's so glad to see that Europe funding body would like to support this giant project, collaborating with so many universities, outstanding researchers to work on this topic. How could we apply robotics in forestry? And I did feel that the EU is leading in this field, and we invited 2 professors from North America to give us a speech, their speeches, and yeah, clearly we don't have this kind of like huge project, and hopefully in the future we can collaborate with each other to really push the robotic implications in the global forestry. So any questions specifically for Matías? And we maybe we can just start the panel discussion. And if you guys have any questions for this part for our speakers, feel free to post your questions in the Q&A. And I will just start with one general question. What do you guys think about the most significant challenges to deploying robotics in forest environments, and how can this be overcome? Any thoughts about this?
Well, if I may pitch in first, I think the wide varieties of forests environments will be a challenge. Like more or less all roads are the same, cars are the same, pedestrians are the same, but forest comes in so many different types that I think that will be very challenging. And in the city, there's always a traversable path because cities have been engineered. In the forest, there's no guarantee that there's a traversable path. And those are the kind of problems which are hard, I find, for machine learning, is when you don't even know if there's a solution or not. Like most papers you see with machine learning, that says, hey, ImageNet, I have 1,000 classes, show a picture, yeah, it's better than human. Yeah, but it's because first of all, the pictures you show it is guaranteed to have one of the 1,000 classes. But that's not once you deploy robots in the real world, it's that goes out the door. All of these out of distribution problems, they will fly us in our face, and also we don't have a lot of data sets. So, and I need data for generalization. So it's a lot of variety, which I think makes it interesting for researchers.
Any other thoughts?
I think I want to just focus on not on technical stuff, because technical stuff can be covered by the Philippe and the Matías. I think the biggest challenge for forestry, for robotic application or something like IST, advanced forestry stuff, is we have very limited expertise in forestry backgrounds, because the forestry students and the professor and researcher, the traditional way, we are more focused on the the change of the speed is really fast right now. So forestry students and professionals often lack the robotics and sensor technologies, and that is prevalent in engineering and robot field. So the challenge is to bridge the gap between the principle of forestry and the technical knowledge required for robotic application as a forestry people. So I'm more than happy to collaborate working with the robotic experts. But at least we need to prepare some kind of, like as a forestry people, how can we prepare for the future direction? Because if the robotic and the older, the ICT technology will be replaced or will be, improved some point of some of the role of the forestry people, then we have to prepare that kind of stuff. I think that is really big challenge for us. And the other one is funding.
Yep.
Yeah.
And it's us, Matías.
Yeah, on my side, if we think about robotics itself, I can show you some very graphical examples of the challenges that exist that are related to what was just said. So if I'm allowed to share the screen briefly,
Yeah,
just a second.
definitely.
Give me 1 second and you will know what I mean. So
Okay.
if I show you things like this, can you see it? Yeah, so this is what happens in practice, right? We have these platforms that are super capable. We would like them to be fully autonomous, but there are still challenges that, from a robotics perspective, that impede us from actually achieving these goals, right? For example, in this case, we deployed the robot in the forest in Finland. It was snowing, it was muddy, the robot got stuck. And one particular challenge from a robotics point of view is like how you actually detect these cases. So the robot was fully kind of submerged, like in the mud. The same, for example, it lost a foot at some point. And for example, last week we deployed the robot as well in the forest in Switzerland, and the robot basically fell at some point because it really got trapped with some undergrowth, and because it was not able to detect this. So we have these pretty robust controllers, for example, that make the robot walk. They're super impressive. You can see the videos online, but there are still challenges that are kind of out of distribution, as Philippe was saying, that will produce these things, and then your mission stops, and then you cannot keep like mapping the forest and getting more traits anymore, right? So I think there are many challenges there when you deploy these robots in these environments that are really challenging. I think we have really good examples in which you can deploy them in structured environments, probably in some factories is reasonable, in some oil and gas spaces is also reasonable. But when you have natural environments, things really change and they're really difficult to describe because the sensors that the robot has maybe are not capable of detecting all of this, or maybe we don't have now the technologies of perception, of navigation algorithms to enable them to actually achieve the stuff that we would like to do in first place. So that's more from the robotics point of view, I would say.
Got it. And actually, I have a follow-up question. So what if we make assumption that we can solve all the challenges, tech challenges now? What kind of other challenges we will face if we want to transfer our technologies to industry, as Matías mentioned in his last slide? And maybe there are cost issues, other kind of issues. What kind of problems you think you will face?
So one thing that always happen when you discuss technology with people, either mining or, it's demonstrate me that what is my return on investment? And most of the time, high-tech companies will go and they says, well, I don't know, just believe me. and then that's the end of the discussion. So there need to be a clear demonstration of return on investment, because if you have a $5 million machine to replace a person which is paid $50 an hour, it's not going to work. So, and oftentimes people, like there was again in the workshop for field robotics, we had Sanjeev who said basically you should not focus on reducing costs but increase productivity. Your machine can now operate 24 hours instead of costing $10 an hour less. So this is the kind of thing that I think at the end of the day is just being counting to make the technology transfer.
Okay. Dr. Wu, as a forester, what kind of technologies you anticipate the forestry guys will be interested in like applying their like the daily workflow to increase their productivity or do some work like human can hardly do?
Yeah, I think the the Matías and Philippe shared their research previously. So even we so I'm really happy to share the year the quarter of the robot roasted the sensor of the year the feed, because if that is real happen in forestry and the price of that sensor is not cheap, and also so because of that reason I'm always looking for like a technology which is real applicable in industry. So I prefer to using LiDAR than I prefer to using stereo sensor, stereo camera, or like a single camera using machine vision technology to identify, you know, like a DVH or tree lines, something like that, because that is way cheaper and way cost-effective way to then like purchasing the high cost of the sensor. So it is really difficult to say, but we need to do both way, like doing the LiDAR or like high spec of the sensor need to be the research in the forestry people. And also in the same way, we have to focus on the practical way, like the using deep learning or machine vision algorithm, machine vision technology with the server sensor is very affordable in apply in real forestry situation. So, but the problem is there is not many experts in forestry. That's true. So yeah.
Yeah, got it. And Matthias, actually, like on your slides, I saw some companies funded based on the technologies they developed to apply robotics in forestry. I just wonder, in Europe, did you see what kind of future do you think like robotics will enter the forest industry or is already entering the forest industry now?
So the feeling that I got from the companies we're working with is that, for example, the Nordic countries are more open to include these technologies. So, for example, we're working with a Finnish company and they are doing robotics solutions. They are interested in kind of having this harvester working, right? So they have this interest to make it happen. So I think in the UK it's less clear, for example, and I don't know the situation from other countries in Europe to be pretty honest about this. So I think it maybe, for example, in other countries, there is like more kind of interest in developing them. On a more general view, the other thing that I want to say that is important for adoption is like solutions should be easy to use, I guess. That is something really practical. And maybe from being a robotics researcher myself makes the stuff kind of, I don't want to say boring, but it's like you develop like this huge technology to make the robot walk by its own, for example. But in the end, it's not important, right? Because you want something that is easy. I would just want to take the robot, bring it to the field, press a button, and comes back with the data I need, for example. Or the same with this interface that we develop all this mapping, SLAM system, multi-session mapping, or all these algorithms to do the online tree detection. But in the end, what people will see and will convince them to use this, it's like the graphical interface that you have on your tablet that is kind of giving you the feedback that you need to do the mission, right? The inventory mission. So that's kind of a gap that I guess that I don't know if it should be solved. I don't think it should be solved at a research level, but it's really kind of transferring the solutions developed in academia to companies, and for example, having this kind of joint projects is a good place to do it.
Okay, got it. Thanks for sharing. And
if I'm allowed, I'd like to jump on Matthias' comment, because first of all, I saw you have a couple of papers and I read that I have to read because it looks super interesting. Because that online tool, this is something very, very interesting, because it's like you tell people, okay, I'm going to sell you a SLAM system, and then they go in the forest, they walk around, and they come back, and they make a map offline, and it doesn't work. And it's like, oh, of course it doesn't work, because you have to use a very specific pattern when you walk, because you want to have lots of loop closure. And they're like, what's loop closure? But having these online tools where as the person walks around, they'll see that, oh, if I do this pattern, my maps improve because I can see it with my eyes. I think these are superb tools to actually democratize this technology, because people people are intelligent. If they have online feedback, they will develop the way how I walk in the forest to get a good map. But if you just hand them a tool and says, this magically makes 3D map and it doesn't work, then it's a black box.
True. And any other
Yeah,
thoughts?
if I can, you can follow up even more. Like, I guess that with all these technologies that we have right now, like language models, we can have better interfaces to interact with these technologies. And I guess that that's also kind of a promising space in which we can exploit them, right? So I guess that we don't have anything in this space right now, but it could be something interesting that somebody can do, I guess.
Yep. And yeah, so let's jump to another question. So looking forward, and what kind of innovations in robotics and AI do you believe will be game changers to the forest sectors in the future? Since I know these two fields evolve very quickly, and there are a lot of new studies maybe occur every day. So a lot of exciting papers, research published online. So any thoughts on this question?
I'll start with saying that self-supervised approach and will be a game changer because, as mentioned, nobody wants to annotate. We don't have the pool resources to annotate the data. Learning by imitation, again, all these things. I think these would be game changer for the forestry because they don't have the budgets, and I think it's one of the area where and also all the multimodality. And when I say multimodality, it's not the multimodality of LLMs where they say, oh, vision and words. It's like, I'm talking about vision, 3D, spectral, polarized, you name it, like radar, even if you want, throw it in there. Like, I think that also will be a game changer when we have all these things. And also Heesung talked about the price of LiDARs. Well, the price of LiDARs are dropping. So also, again, if you can have like reliable LiDARs for $100, then of course, every company will install it. So I think these, at least from my point of view, I think these are the future game changers.
Definitely. Any thoughts on this question, Dr. Woo?
I didn't capture your question.
Okay, so looking forward, what kind of innovations in robotics and AI do you believe will be game changers for the forest sector?
I think this is my personal opinion. So
yeah,
the character of the forest industry and forestry is very conservative. So I think technology is already improved, and there's the fast. There is so fast. So I think the most important thing is we should to change. We need to change. Like as a forestry people, we have to open mind to adopt this kind of technology, and we need to like testing and the couple years ago, the movie Iron Man, and the movie he has the Jarvis like his or like own like AI system. But right now, everybody can use ChatGPT for their like a support or whatever. But in here, this kind of we are living this kind of world. So we are still working in the very, dangerous situation, and we went to the field work, and we are going to the nature. But anyway, we have to some kind of, change. We need to change to adopt this kind of technology to improve more efficient way and more safety way, and also there is like as I mentioned before, like there is lots of we have lots of challenging for aging, and there is lack of interest about the young people. So to overcome this kind of issue, we have to very open mind to adopt this kind of technology. I think the attitude from the outside has to be need to be changed. I think so. Yeah. Maybe
true.
this is a wrong answer, but this is my opinion.
No, I think that's a great answer. Since I'm a forester and a forestry student, definitely we should open our minds to hark these new technologies. Sometimes some technologies are ready to be used, and we just don't use them. Sometimes it's not about cost. Maybe we all know that it can potentially increase our productivity or we know it will be the future of forestry, but for now we're just a little bit afraid of like using these technologies. I don't know, maybe some phobia, but I think that's definitely something we need to change, right? And we should like try to keep our like the step with and just like follow the trend, follow the technological innovation. Matías, do you have any thoughts on this question?
Yeah, I feel like I'm gonna diverge from what Heesung was saying, so that's what I was like, should I just continue or not? But okay, but if I fully agree with what he was saying.
Panel discussion.
I fully agree with what he was saying, but maybe coming back to maybe the technical part of it, I guess that I fully agree with what was said. The other thing that I think is really important and I'm really impressed with is simulation tools. And for example, particularly reinforcement learning. That's what I was saying, that I was going back to the technical aspects. Because all the work, for example, done by my colleagues at ETH, in which they simulate these big machines so they're able to control them and kind of handle all these cases, I think is pretty impressive, and also has like a lot of promise, because maybe you have some old machinery that you cannot model that accurately, and you can simulate it and kind of make it learn from simulation, which I think could be quite interesting. But yeah.
So simulation, we've done some work with simulation. Vincent has worked with that. And it gives you some, I know they say like simulation is doomed to succeed, but there's always this symptomal gap. I know you know about it. And I just feel like at the moment, maybe we should just start equipping the current equipment with tons of sensors, and just, do it the Tesla way, where, each car is used to collect data. And then we just start leveraging that data. And the thing is, every time somebody cuts a tree, they just annotated a tree for you. So we're cutting billions of trees every year. And right now that data is going to waste. It's not being used. And it frustrates me to see that. So I think one way is, to just start, Tesla, they put all the cameras before doing self-driving cars because they knew they were going to do it. How about all the manufacturers put cameras in their systems, and we start, pulling that resource, pulling that data, and then start doing research with it.
So I guess that connects to what Heesung was saying, right? So it's really about if you have the view that this data could be used eventually, and it's really about this adoption. Companies, if they could see the value of this, they could put the sensors and maybe even offer the data, sell the data, I don't know. And it could be used for these things, but it's really about kind of this gap between the potential things we could do, but having, on the other hand, the people interested and seeing the value, so they will be kind of open to do this kind of
Sometimes maybe it will be a challenge for persuade companies to collect data and use that for research purposes, since they're doing that mainly for commercial purposes to make money. And actually, we need to make them to see the values of collecting data for us and provide them to the academia, maybe even publish online for public access. Yeah, so like I got one last question for our last 5 minutes. So how do you guys envision the future workforce in forestry with the increasing integration of robotics and AI technologies?
Well, I guess I see the future workforce will be one that, raised, this is the generation of the cell phone. So it's like they already very data smart. And I think it'll be a well-connected workforce where they might work in the field a little bit, but also work remotely. And I believe they become managers of machine rather than operators of machine. I still think we will need people to go be trained to cut trees, because to operate, to make sure that your robot operates properly, you need to know how to cut trees. And so the thing is, they'll learn to do it, and then they'll just let the robot do it. But I think it's important. So I think it will be a lot more fun job, because there'll be a lot less repetition. because machines are good at repetitive tasks, but they are not good when there's like a out of distribution event or a long tail event. And this is where humans are very good at, and it's what makes the job interesting in some sense. So I think they'll be very happy at their job, and they'll be very productive because they'll be managing 15 machines, and they'll still have the chance to go in the field because I think people still like to go in the forests. So it will be very flexible. They will not be contained in that prison cell which is the cabin where they cut trees. They'll be just all over the place. So, and yeah, that's how I see the future workforce.
Yeah, yeah. And there are a lot of smartphone apps which can help us to collect data in forestry. And for example, the iNaturalist, you can simply take a picture of a plants and do the identification. And I know a lot of people are working on this kind of subject to help us to collect data more efficiently with current technologies we are using daily. Dr. Wu, do you have any thoughts on that?
Yeah, I think the future workforce in forestry, I think that the integrated with the robot is the most important thing is we can increase like a safety issue, like we can reduce. So we can enhance the safety because the use of the robot for dangerous area or hazardous task that can be that will improve the worker safety by reducing the exposure like human like dangers. So I think the safety is the most important thing for the introducing the robot in forestry field. And the other one is like as Philippe mentioned, lots of people are asking me about what forestry worker will do when the robotic come into the forestry field, forestry industry. And I said I agree with Philip. The role of the forest worker will be changed. So job will be transformed to from the operator to the robot manager and robot maintenance or whatever, something like that. And I think that can be the the more helpful for the man and woman can actually forestry is very highly demand for the physical demand work. So if we are introducing like a robot application in forestry, the woman can be support and the more like a physical support from the robot kind of application. So it is much easier to people to get some access to that kind of dangerous place, and the people's role, their skill shift will be the from the collect data from the manual measurement to the a data analysis and just maintaining advanced robotic system and or AI programming, something like that. So I think this will be the future workforce with the robotic. Yeah.
Yeah, I don't think there's that much to be said after that. I think I fully agree with what was discussed so far. Yeah, I feel like I agree with all the thoughts that it should be more like a supervision rather than doing the actual work, and also hope that with all this data that we get, because I think it's going to be definitely data driven, we can be less disruptive as well. Because we can be more careful, we can kind of measure more things, we can kind of quantify the impact we're doing. So I think on that side, I also expect that all this data that we're getting is not just like taking the people kind of towards the supervision, but also kind of enabling like a more sustainable way to do forestry, I guess.
Yeah, totally get it. And actually, there is one quick question from Lee. And so for you guys, will it be helpful for young forestry students to focus more maybe on coding, deep learning, this modern technologies rather than traditional forestry knowledge? What do you guys think about it?
I think ChatGPT will support the coding. So
yeah,
I think the the most important thing is the understanding about the problem. And the idea about how to draw the big picture about if the student is a graduate student, I think so. Of course there is required for understanding coding or deep learning algorithm as a forestry student, and it must be really helpful for to better understanding about without any knowledge. But I think just it is really difficult answer, but yeah.
No, it's not. It's not like I think we should like as young students we should need to like to still get as much as like the forestry knowledge we can. We also need to learn a lot of like practical skills in case maybe there will be more like the job opportunity in the futures which require this kind of skills.
Yeah, with based on your forestry knowledge, plus with like coding and deep learning, that kind of skill can make a better, opportunity. That I think that's for sure.
Yeah, yeah. And so thank you so much for attending today's webinar. And I have already recorded this session, and I will post it on LinkedIn in the future. And Matías, Philippe, Dr. Woo will also share their slides with me, and I will also post them on LinkedIn. And same to follow up our YouTube account. You can also so this materials post on that. So thank you so much again. They are all wonderful presentations and great thoughts in the last part of panel discussion. And hopefully we can see more and more robotics innovation and applications in forestry in the future. And we also hope that maybe in the future in North America, we can have kind of similar project as a DigiForest in EU. And maybe we can even have a giant international collaboration research project to promote this field. So yeah, thank you so much again. And that's the end of our webinar. And maybe see you guys next time. Bye.
Yes.
Thank
Thank
you.
you, Walter, for
Bye-bye.
hosting.
Have a good day.
Thank you.
Have a good day.